Hello everybody. Welcome to Bulk Carriers presentation that was created in an effort to provide a better understanding for bulk carriers operations. Content: Archimedes Principle, Standard Hull Terms, How Ships Flow, Ballast, Constant, Displacement, Deadweight, Lightweight, Carrying Capacity of a Vessel, Draft Survey, Weight Ships, Limiting Factors on Stowage Plans, Stowage Factor, Stability, Grain Stability, Grain Healing Moment, Stowage Plan, Loadicator. Let's start with Archimedes' Principle. Archimedes' principle states that the upward buoyant force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. Archimedes' principle is a law of physics, fundamental to fluid mechanics. It was formulated by Archimedes of Syracuse. Let's continue with some standard terms for ship's hull.
The following are the standard terms used to describe the hull of a ship, even before it is put into the water. These first few terms are fairly basic. Depth is the height of a hull from the highest point of its main deck to its lowest point. In the other direction, a ship's beam, or breadth, is its width at its widest point. The center line is a vertical plane that runs the length of the ship at the midpoint of its beam, and the baseline is a horizontal plane perpendicular to the center line, located at the lowest point of the hull. The keel is the principal structural member of a ship, running lengthwise along the center line from bow to stern, to which the ship's frames are attached. The lowest point of the keel, or K, is the point from which vertical distances are measured on a ship. K is located at the intersection of the center line and the baseline. The water line is the intersection of the surface of the water a ship is floating in with the sides of the ship's hull. When a ship is designed, the naval architect determines the design waterline, or DWL, that represents the waterline of a ship under full load or maximum draft conditions on an even keel. The forward perpendicular, or FP, is a vertical line drawn at the intersection of the design waterline and the foreside of the stem of the hull. The after perpendicular, or AP, is a vertical line drawn at the intersection of the design waterline and the aftmost point of a ship's hull. For most commercial vessels, this is generally where the rudder post is located. Midships is the horizontal point halfway between the forward and aft perpendiculars, and the length between perpendiculars, or LBP, is the total horizontal distance between the forward and aft perpendiculars. Length overall, or LOA, is the total length of a ship at its longest point. Note that this may be a little longer than the LBP because a ship can extend slightly past the perpendiculars. Distances on board ships are measured in one of three directions: longitudinally, transversely, and vertically. Longitudinal is the horizontal direction along the length of a ship. Longitudinal distances are measured from one of three places: the forward perpendicular, the aft perpendicular, or midships. Where longitudinal measurements are taken from will vary from ship to ship. Transverse is the horizontal direction across the beam of a ship. Transverse distances are measured port or starboard from the center line, with one written as a positive distance and the other as negative. It is not standard which is which, however, and this varies from ship to ship as well. Vertical distances on a ship are measured upward from the baseline, or lowest point of the keel. With these terms in mind, we can now look at how a ship interacts with the water. These concepts are the foundation of stability and trim. What holds a ship above the water is the force of buoyancy, a force that equals the weight of the water the ship displaces. Displacement is the amount of water pushed aside or displaced by a ship when it is floating. A ship's displacement is always equal to the total weight and is measured in tons. Depending on your vessel, ship stability can be calculated in either the metric or imperial system, so you must be familiar with both. Displacement was first understood by the Greek thinker Archimedes over 2,000 years ago. The king of Syracuse had asked Archimedes to determine if a crown he had commissioned was pure gold or if the jeweler had cheated him by mixing in some lesser metal. While he was still thinking about it, Archimedes noticed the water in his bathtub rise as he stepped into it. "Eureka!" he shouted and ran naked into the streets in his excitement. By using displacement, he understood that he could measure the exact volume of the crown. This allowed him to find its density, telling him if the metal was pure or not. It wasn't. Draft is the vertical distance between the waterline and the lowest point of the hull. A ship's draft can be found or taken by reading the draft marks that are welded onto a ship's hull, forward and aft. Tons per inch of immersion, or TPI, is the number of tons necessary to change the draft of a vessel by 1 inch. In the metric system, this is tons per centimeter of immersion, or TPC. Load lines are marks welded on the side of a vessel's hull at midships, showing the draft under maximum safe loading conditions. This mark is called the plimsoll mark. If a vessel is overloaded and its draft is deeper than its load line, it is unsafe and is in violation of the International Load Line Convention. It will be subject to fines or other legal actions, and its insurance is void. Trim is the difference in draft, forward and aft. The trim of a vessel can be found by reading the draft marks on its hull. These draft marks are placed as close to the perpendiculars as the shape of the hull allows. A vessel's freeboard is the vertical distance between the waterline and the highest watertight deck of the hull, usually the main deck. Freeboard is important because it is part of what determines the volume of the space above the waterline. The waterplane area, or AWP, of a vessel is the horizontal intersection of the waterplane and the vessel's sides. The bigger a vessel's waterplane area is, the greater the surface of the hull is that buoyancy will be acting against. For this reason, in the case of two vessels with the same weight added, the one with the greater waterplane area will have a smaller change in draft. As a vessel rolls in the water, its waterplane area increases as long as there is freeboard available to add to it. The larger a vessel's waterplane area becomes when it rolls, the more buoyant force it develops. This is why freeboard is indicative of a ship's reserve buoyancy, or additional buoyancy at larger angles of roll. Longitudinal center of flotation, or LCF, is the geometric center of the waterplane area. The LCF is the point about which the vessel trims. Note that the LCF is not necessarily located at midships. Its location is determined by the shape of the waterplane area and the trim of the vessel. Stability is the tendency of a vessel to right itself. When a vessel is tilted by an outside force, such as wind or waves, and it returns to its original position, it has positive stability. If it does not, it has neutral or negative stability.
And now, how do ships flow? When a boat displaces a weight of water equal to its own weight, it floats. Every ship must be designed to displace a weight of fluid at least equal to its own weight. A 10,000-ton ship's hull must be built wide enough, long enough and deep enough to displace 10,000 tons of water and still have some hull above the water to prevent it from sinking. It needs extra hull to fight waves that would otherwise fill it and, by increasing its mass, cause it to submerge. As we can see at the picture here, by multiplying the 150 meters length times 30 meters beam times 20 meters depth times 0.7 block coefficient ratio, we get the volume of the ship in cubic meters. So, the volume of the water displaced is equal with 63,000 cubic meters. By multiplying the volume of the water by its density 1.025 here, we get the weight of the ship in metric tons. As per Archimedes' principle, this vessel weighs 64,575 metric tons in salt water with density 1.025. What is displacement? And what is dead weight? Displacement tonnage. Delta displacement tonnage is nothing more than the total weight of the volume of water a ship displaces when it is sitting in the water. Imagine you had a large bucket filled to the brim with water. Now, suppose you gently placed a basketball in the bucket, causing some of the water in the bucket to spill out. Once the basketball had stabilized and was freely floating in the bucket, the weight of the water that was displaced is equal to the displacement or weight of the basketball. Deadweight tonnage (DW). Deadweight tonnage is the weight in tons of all the cargo, fuel, dry provisions, supplies, etc. carried on board the ship. Deadweight tonnage is a good indication for ship owners and clients of how much revenue the vessel can generate. Lightship. Lightweight tonnage. Lightweight tonnage is best described as the weight of the ship when it was built in the shipyard, including all framing, machinery, decking, etc. However, lightweight tonnage does not include the weight of any consumable such as fuel, water, oil, or supplies. The following formula determines the dead weight of a vessel. Displacement. The total weight of the ship minus the lightship, the weight of the vessel as was delivered by the shipyard. It's equal to dead weight of the vessel, the capacity of the vessel. Bunkers, ballast, fresh water and constant weights occupy a part of the dead weight of the vessel. Due to sagging or hogging of the ship, there is a small loss of the capacity as well. The capacity that is left is available for cargo. As we understand here, once we know the displacement of a vessel, it is easy to calculate its dead weight. To calculate the displacement of the vessel, we conduct draft surveys. Draft surveys are convenient and economical means of ascertaining the quantity of cargo loaded or discharged from a ship by reading the vessel's drafts. In principle, draft surveys require only a measurement of the water displaced by the vessel before and after the cargo is transferred, along with a measurement of the water's density. Water displacement is measured through draft marks on the ship and converted to a volume, using draft tables. Once a vessel arrives to the berth of loading, a draft survey will be conducted to calculate the initial displacement delta before loading operation begin. After the completion of loading operation, a final draft survey will be conducted for the calculation of final displacement delta. So, by using the formula, initial displacement plus cargo, plus or minus consumables, during loading period, we get the final displacement. We weight ships all the time. Let's watch a video.
Stupid as it sounds, we actually weigh ships all the time. And there are a number of reasons why we do it. Imagine you want to move a lot of cargo. Maybe you've got a huge amount of coal that you want to sell. You know roughly how much you have, because you kind of measure your pile. But when someone's going to be buying 20,000 tons at $100 per ton, they want better than a rough estimate. They want to know exactly how much they're paying for. Now you could weigh the whole pile of coal, but that's not really practical. You could weigh it as you lift it onto the ship, but again, that would take ages. The simplest solution is actually to just weigh the ship. You can weigh it once before loading, and then again immediately afterwards, the difference giving you the amount of cargo that you've loaded. And what about a passenger ship? Do you weigh every passenger and bag as they board? Actually no, we make a rough estimate and then we weigh the ship to check the numbers. Well, not actually using a set of scales. I doubt there's a set anywhere in the world capable of weighing 500,000 tons. Instead, we turn to our friend Archimedes. Effectively, a ship will displace its own weight in water if it's going to remain afloat. To weigh the ship, we just need to know how much water it displaces. Ships and boats are designed by naval architects who model the exact shape of the hull. They give us a set of tables that we use to work out how much cargo a ship can safely carry. For different weights, these tables tell us how low she will sit in the water. Now the beauty of maths is that it works both ways. Instead of working out how low she will sit for a given weight of cargo, we can work out the weight from how low she is sitting. So how do you know how low a ship is sitting in the water? If you've been up close with any ship, you probably noticed the numbers written on the side. These are the draft marks and they measure how low the ship is sitting. The numbers count up from the bottom of the ship, starting at 0 at the keel and continuing up to the deepest draft she could sit at. Most will give metric readings, effectively giving you the draft in meters, though there are countries that do give the draft in feet. I believe the USA is the biggest one that's still doing that. For metric draft marks, you'll notice they sometimes give whole meters, and then they seem to count up in 20 centimetre increments. Others give decimeters instead. Of course, 20 decimeters is 2 meters, 30 decimeters is 3 meters, and so on. Again, these go up in 2 decimeter increments, effectively measuring every 20 centimeters. But if you look a little deeper, they're actually counting in 10 centimeter increments, and that's due to the height of the digits. When the water is at the bottom of the number itself gives the draft. When it reaches the top of the number, it's halfway up to the next digit. In this case, the bottom of the number measured 2 meters, 20 centimeters. The top of the number is 2 meters, 30 centimeters. It all seems very simple, and it is when the ship is sitting perfectly upright and perfectly trimmed. Unfortunately, this is virtually never the case. So, to help us, draft marks are located at 6 points around the ship. You've got the forward port and starboard, midships port and starboard, and the aft port and starboard. Reading all 6 of them will give you a much better idea of how a ship is sitting in the water. It will tell you about any bending in the hull, and that's actually normal, and it's so normal it's named hogging and sagging. If you do read all 6 drafts, you can actually then calculate an average, which you can work with. That average draft then allows you to work out the volume of water that's been displaced by the shape of the hull, using those loading tables that we talked about earlier. Finally, to convert that volume into a weight, you just need to multiply it by the density of the water. Now we typically work with 2 different densities. Seawater has a density of 1025 kilos per cubic metre, and freshwater's got a density of 1000 kilos per cubic metre. Due to the variations, we actually measure the density of water that the ship is currently sitting in. Finally, to work out the overall weight of the ship, you just take that volume of water that you've calculated your ship has displaced, and you multiply it by the density of the water that you've just measured. It might not be as simple as just putting the ship on a set of scales, but scientifically, it's the simplest way for us to weigh a ship.
And now let's continue with stowage plans of a ship. A stowage plan needs to meet multiple criteria.
The structure of a typical bulk carrier consists of a single-deck ship, fitted with topside tanks, a double bottom, hopper tanks, and side shells with vertical frames, corrugated bulkheads, and hatchways above. The holds are a series of large spaces separated by transverse bulkheads. Despite all this steelwork, the ship is not a rigid structure. In fact, For it to function effectively, there must be a degree of flexibility. However, overloading any one of the holds will cause excessive stress to the structure of the vessel. And if a cargo is poured into one end of a hold and piles up, the pressure acting on the transverse bulkhead will increase. Likewise, if cargo is unevenly distributed away from the vessel's center line, this will induce twisting and the subsequent warping of the hull structure, as well as placing stress on the transverse bulkheads. Therefore, the agreed loading sequence should be followed precisely, and cargo must always be stowed and trimmed appropriately within permissible limits. Whilst at sea, there are further forces that act upon the hull, which must also be considered. A ship has its own weight, made up of its structure, machinery, crew, stores and effects. Adding to this, by filling and emptying the cargo holds and ballast tanks, will generate additional shear forces and bending moments. Put simply, shear force is caused by two opposing forces acting against each other. There is a downward vertical force, which comes from the weight of the hull and cargo, and an opposing upward action, which is the buoyancy of the vessel. Shear forces occur when these forces are not in balance at every point along the length of the ship. A bending moment is a force that bends the vessel along its length. If weight is concentrated in the middle of the ship, bending of the structure will cause sagging. And if weight is concentrated at opposite ends of the ship, this will result in hogging. At sea, the ship is subjected to a continuous cycle of these varying forces and the changing wave pressure acting on the hull. If handled with care, the ship's structure is designed to withstand maximum permissible shear forces and bending moments. Shear force and bending moment calculations should always be prepared prior to any cargo handling or ballast water operation. The calculations must be accurate, because if the maximum permissible limits are exceeded, the ship could be at risk of structural failure. Handling a bulk carrier with care requires understanding and the full cooperation and expertise of both ship's crew and shore personnel. Both parties have a number of tools at their disposal, which assist with the correct loading, stowage, and discharge of cargo. Aboard ship, there should be an approved loading manual. This must give the ship's designed cargo loading conditions and distribution, as well as stating the maximum permissible shear force and bending moment limits. These limits are set for both harbour conditions, when the vessel is in port, and at sea conditions, which take into account the additional stresses of the ship moving in a seaway. The ship should also be equipped with a designated class-approved loading computer and appropriate software. As these systems vary, ship's officers must be familiar with and competent in the use of the equipment specific to the vessel. Ship's officers also need to be capable of producing an accurate loading or discharge plan. This must take into account ballast water management and stability, as well as the vessel's shear force and bending moments at each stage of any loading or discharge sequence. The calculations must observe the permissible harbour and at sea limits. And if plans deviate for whatever reason, the figures must be recalculated before acceptance.
It's 54% maximum.
Aboard some vessels, hull stress monitoring systems are fitted. These can provide ship's officers with real-time indications of the effects of shear force and bending moments, both at sea and in port. As they're often linked to the loading computer, they can highlight any deviations from the loading plan or the maximum permitted stress limits, allowing corrective action to be taken. There are also mandatory regulations and guidance in the form of 2 codebooks, which must be aboard every bulk carrier. The International Maritime Solid Bulk Cargoes Code, the IMSBC code, is designed to help ships' crew identify and correctly handle certain cargoes that could present a hazard, such as liquefaction or chemical reaction. The individual schedules not only describe the particular characteristics of these cargoes, they also provide general reference information relating to bulk densities, stowage factors, and trimming procedures. The Code of Practice for the Safe Loading and Unloading of Bulk Carriers, or Blue Code, is found in the supplement section of the IMSBC Code. The Blue Code provides guidance to ship's masters and terminal operators on the safe handling, loading, and unloading of solid bulk cargoes. Ashore, the Blue Manual supplements the Blue Code and provides further detailed guidance for terminal operators. By referring to these codes and by understanding bulk carrier design and operating limits, both the ship's crew and shore personnel become key partners for the safety of the vessel. And as with any successful partnership, establishing good, clear communication early in the relationship is vital. Once a charter or commercial voyage has been fixed, it's important that the ship is provided with preliminary information about the prospective cargo and terminal, so that loading or unloading can be planned. If applicable, this information will be checked against the IMSBC code, so that ship's officers are fully aware of the properties or handling requirements of the intended cargo. The loading plan should also take into account the requirements of the IMSBC code, as this may have a bearing on stowage and segregation. But in all cases, the preliminary shipping information must be received in sufficient time to allow an accurate loading or discharge plan to be produced. Likewise, terminal staff will require information about the ship in order for them to put in place their own preparations for cargo handling. Therefore, a two-way information exchange between ship and shore must take place prior to arrival. This is to ensure the upcoming cargo operations are conducted safely and within the operational limits of both vessel and terminal. This information exchange should be laid out as specified by the Blue Code and must be clear, understood, and agreed by both parties. As early as possible, the master should provide the ship's ETA and particulars, details of any ballasting or deballasting requirements, along with a preliminary loading or discharge plan. This plan should be prepared in a form such as that laid out in Appendix 2 of the Blue Code. Amongst other items, it should include the quantity of cargo and the number and order in which holds are to be worked. The ship should also provide details of its mooring and gangway arrangements, as well as confirming that holds into which cargo is to be loaded are clean and free from previous cargo residues. For its part, the terminal should provide information such as the name and availability of the berth, the estimated times for berthing, the estimated times for the completion of loading or discharge, any characteristics of the cargo handling equipment, expected loading or unloading rates, and the name and contact details of the nominated terminal representative. Further factors to consider are the minimum depth of water alongside, berthing arrangements, and the availability of tugs. Any information given by the terminal relating to tides, the water depth at the approach and departure channels, as well as the water depth at the berth, must be accurate and complete to assist safe navigation. And the ship's arrival condition and maneuverability should always be considered. For example, a lightly ballasted ship can become vulnerable during navigation, as both rudder and propeller efficiencies are reduced, and the windage is increased. In these circumstances, the ship's ability to maneuver safely is reduced, particularly in high winds and strong currents. And with restricted vessel handling, the chances of navigational error, collision, or grounding increase. So it's vital that any proposed arrival or departure drafts, as well as any restrictions or time requirements relating to deballasting operations, are checked and agreed by both parties. And any conditions applied must always take into account the capabilities and safe working limits of both the ship and terminal.
We have 15.5 meters, okay?
Depth.
Yeah.
Once alongside, the terminal's nominated representative and the master, or chief officer, must conduct a meeting before starting cargo operations.
Leave at high water.
At this point, the final cargo plan is discussed and approved, and a joint ship-shore checklist completed and countersigned by both parties.
That is the telephone number.
Amongst other items, this checklist will consider that an agreed system of communication along with designated liaison contacts aboard and ashore has been established. Any restrictions on taking bunkers have been put in place, and that the atmosphere is safe in the holds that may require access. Check, too, that the shipper has provided the information on the properties of the cargo, and that any testing certification relating to cargo characteristics is complete and accurate. Masters are ultimately responsible at all times for the safe loading and unloading of the ship. This includes controlling the safe and efficient synchronization of cargo operations and ballast water operations.
We have this information. We have this information.
Both the terminal and ship should ensure the sequence of holds to be worked has been clearly identified and agreed.
1,000 per hour, maximum.
And the ship must ensure the cargo loading or discharge plan has been calculated for all stages of the operation, including at times of ballasting or deballasting. For this reason, it's imperative that the loading or discharge plan has been agreed and countersigned by both the ship and the terminal, and that communication and agreement is maintained at all times. If ship's officers are not satisfied with the cargo handling activity, or there is a sudden deviation from the agreed plan, the master should be informed immediately.
By that time we already need to sail out, so they're asking if that's okay for us.
The master must stop the loading or discharge if the cargo distribution could adversely affect either the stability or the stresses on the ship's structure. Cargo distribution along the ship's length has a direct influence on the bending moments and shear forces. Evenly distributed cargo in all holds is usually adopted for low-density cargoes, such as coal and grain. This is called homogeneous loading. Large bulk carriers sometimes stow high-density cargoes, such as mineral ores, in every other hold. This is called alternate loading. When high-density cargoes are stowed in this manner, the weight of the cargo in each hold is approximately double that carried in a homogeneous load distribution. As a result, this requires a vessel to be strengthened and classified for this loading configuration. And under SOLAS, vessels over 150 meters and more than 10 years old are forbidden to use alternate loading unless certain conditions are met. Block loading is where cargo is loaded in two or more adjacent holds, with neighboring holds remaining empty. This method is often adopted when the ship is part loaded or carrying more than one commodity. It requires approved conditions as specified in the loading manual. And to avoid overstressing the hull structure, careful consideration should be given to the amount of cargo loaded in each hold and to the sailing draft. Regardless of loading method, at all times, the hull stresses should be kept below permissible limits. Loading rates and deballasting rates must be monitored throughout to ensure that the ship's structure is not overstressed and that shear force and bending moment limits are not exceeded. It's crucial, therefore, to monitor the ship's condition closely during cargo operations. Ship's personnel must carry out draft surveys at regular intervals to check the calculated ship's loading condition, the cargo weight, and its distribution. The recorded readings should be checked against the loading plan. This information, together with loading rates, ballast synchronization, stress and displacement calculations, all help to balance the forces acting on the hull. Officers on watch during cargo operations must ensure terminal staff follow the agreed plan. If there is any deviation for whatever reason, corrective action should be taken. If necessary, cargo operations should be stopped and the plan modified, ensuring that the stress and operational limits of the ship are not exceeded. For example, conveyor belts offer a very efficient method of loading, with rates varying between 1,000 and 16,000 tons per hour. And in some ports, rates can even go higher. This stretches the efficiency of the ship's ballast water system, making the synchronization between deballasting and loading difficult. In these circumstances, the ship and the terminal should agree that if deballasting becomes out of step with cargo operations, loading should be suspended until the deballasting operation has caught up. During both loading and discharge, mechanical equipment may also damage the ship's structure. Whilst discharging, the use of grabs or hydraulic excavators can cause damage to the hold structure or its protective coatings. And during loading, it is the terminal's responsibility to alert the master to any individual grab loads or pours that are large or heavy, where there could be the risk of a high-impact drop. These could potentially damage hopper sides and tank top structures or stress the ship's hull. For this reason, particular care should be taken at the start of any loading operation into empty holds, especially when loading steel and scrap metal cargoes. Officers and crew members should be on the lookout for damage during cargo operations at all times. Manhole covers or gratings for bilge wells should be checked that they're present and intact. And any damage to the ship's structure caused by terminal handling equipment must be reported immediately. Guidance on damage reporting procedures is contained in the Blue Manual, Annex 3. But many companies will also have their own procedures. Loading equipment and conveyor designs vary. The time it takes to halt the operation must be taken into account to avoid overloading the ship. During the last stages of loading, the master should advise the terminal when final trimming has to begin in order to allow time for conveyor runoff. Trimming requires close supervision, and where applicable, it should be carried out in accordance with the requirements of the IMSBC code. For instance, some cargoes have a specific angle of repose. This is of significance with free-flowing, non-cohesive cargoes, liable to shift if not correctly distributed. In the case of discharge, The terminal representative should advise the master when unloading is considered as completed from each hold. And close supervision should be kept on the final stages of the unloading operation to ensure that all cargo has been discharged and holds cleaned as appropriate. On completion of any cargo operations, the master and terminal representative should agree in writing that the ship has been loaded or discharged in accordance with the plan, including any agreed variations. Any damage that has been occurred should also be recorded and noted by both parties. As terminals seek to maximize throughput and load vessels ever more quickly, the chances are that more mistakes will be made. The safety of a bulk carrier is in the hands of many individuals, both aboard ship and ashore. But the stresses and pressures are not just felt by the people involved. The very ship itself can also suffer from stress and fatigue. And just like people, bulk carriers need to be handled with care and respect.
And now, what is stowage factor? Stowage factor, SF, it is expression which indicates the cubic capacity, space, that 1 ton of cargo will require. Stowage factor is expressed in cubic meters per ton or cubic feet per ton. Iron ore 0.4 to 0.5 cubic meters per ton. Coal 1.2 to 1.4, grain 1.2 to 2.0, bauxite 0.7 to 1.0, steel product 0.3 to 0.6 cubic meter per ton. Stowage factors are approximate values, and the actual space taken up by a parcel of cargo will depend on the care taken in stowing it, the shape of the compartment, etc. Stability. Meta center and center of buoyancy.
A vertical downward force of gravity which is equivalent to the weight of the body, W, acting at the center of gravity, G, and an upward vertical buoyancy force, FB, which is equal to the weight of the water displaced by the immersed body, which passes through the centroid of the displaced volume of water, that is, the center of buoyancy. Now, for a floating body to be in equilibrium, the buoyancy force should be equal to the weight of the body. Also, the center of gravity and the center of buoyancy should lie on the same vertical line, called the center line, BG. Now, if a body undergoes an angular displacement, say in the rightward direction, then we see that the volume displaced is larger in the right side. Thus, the center of buoyancy shifts towards the right from B to B dash, and a couple is formed which tries to rotate the body. Here, the point of intersection of the vertical line through the new center of buoyancy B dash and the center line BG is termed as the meta-center of the body, and the distance by which the meta-center lies above the center of gravity of a floating body is known as the metacentric height, GM, which is given by. Depending upon the location of the meta-center, a floating body possesses 3 types of equilibrium. They are stable, unstable, and neutral equilibrium. When M is above G, then in this case, a restoring couple is formed by the buoyancy force and the weight of the body, which tends to turn the body to its original position. Thus, the body is said to be in stable equilibrium. Now, when M is below G, then in this case, an overturning couple is formed by the buoyancy force and the weight of the body, which tends to sink the body from its original position. Thus, the body is said to be in unstable equilibrium. And when M coincides with G, then in this case, the line of action of buoyancy force and the weight of the body are collinear and passes through the same point. Due to this, the body neither returns to its original position nor increases its displacement further. Thus, the body is said to be in neutral equilibrium.
Carrying grain. One of the most difficult and dangerous cargoes to carry in bulk are grain cargoes. Grain has the tendency to shift. This shifting has adverse effect on stability. Most grains have an angle of repose, slip angle, of about 20 degrees from the horizontal, which means that if the ship rolls more than 20 degrees, the cargo will shift. Then this happens, the ship will develop a large list lying on her side and still rolling. That will obviously cause a greater shift of cargo, which in turn will capsize the vessel. Most authorities therefore request that the master proves that his ship is capable of remaining stable even if the grain cargo shifts. This is done by the compiling of the grain loading form, which fully outlines the ship's stability at the worst condition on passage. Because grain cargoes are liable to shift, heavy emphasis is placed on the stability of ships that carry them. The main reason is the variation in the types of grain, including its size, and its ability to develop a free flow state when loaded in bulk. To avoid shifting of cargo, the grain surfaces must be reasonably trimmed. The cargo should be trimmed so that all spaces under deck and hatch covers are filled to the fullest extent possible. When untrimmed, the cargo should be trimmed within the hatchway but may be left at its natural angle of repose on the surrounding area of the hatchway. This table shows the allowable maximum healing moment due to shift of grain which satisfy following conditions. 1. The angle of heel due to the shift of grain, theta I, shall be not greater than 12 degrees or the angle at which the deck edge is immersed, whichever is the lesser. 2. The net or residual area, alpha R, between the heeling arm curve and righting arm curve, up to angle of heel, of maximum difference between the ordinates of the two curves, theta M, or 40 degrees, or the angle of flooding, theta F. Whichever is the least, shall be not less than 0.075 meter radians. 3. The initial metacentric height, after correction, for the free surface effects of liquids in tanks, GOM, shall be not less than 0.30 meters. The allowable healing moment shows the maximum to be sufficient to comply with the International Grain Code. Grain in cargo hold acts like water in the bottle. Especially when weather conditions are bad, it is even easier for the cargo to shift due to vessel rolling. Imagine a bulk carrier loaded with 70,000 tons of grain in a weather like this. So now we can understand the importance of trimming and stow the grain cargoes properly and according to the rules. Miscalculation of ship stability can cause disastrous events. And now, it's time to take a look in a real stowage plan. This vessel will load from New Orleans an estimated 68,740 metric tons of soybean for discharging in Dalian. The vessel will arrive in New Orleans with draft 5.5 meters forward and 8 meters aft, 2.5 meters trim by stern. After loading completion, the vessel expected to depart from Mississippi River with draft of 13.15 meters forward and 13.50 meters aft in density 1 of fresh water in the river. The vessel expected to arrive in Dalian after a sailing for almost a month with draft 12.90 meters forward and 13.00 meters aft in density 1.025 salt water. Here we can see the air draft of the vessel in ballast and laden condition. The air draft of the vessel is an important information for vessel's operations. The air draft of the vessel is the distance from the surface of the water to the highest point of a vessel. In case of loading, air draft is the distance from the top of hatch coaming to the highest point of the vessel. And below the stowage factor of the cargo, expressed in cubic feet per metric ton. In this line we have the quantity of cargo in each cargo hold, expressed in metric tons. Right below, the percentage of each hold's capacity that will be loaded. As we can see here, all cargo holds are 100% full except cargo hold number 4, that is 75% full and is called slack. Let's continue with these remarks on the stowage plan. Mentioned cargo quantity is the maximum theoretical lifted quantity as per charterer's request. Final loading quantity is always subject to cargo actual stowage factor, vessel stability, trim, stresses, sagging or hogging, cargo reflection, draft restrictions, actual water density, salinity in the load and discharging ports, bunkering, amendments and alterations. As I already mentioned, the stowage plan is pre-calculated according to the estimated figures that are given to the master of the vessel by the charterers. This table shows the quantity of ballast water in each ballast tank. For example, the water ballast tanks number 2, port and starboard, is filled with 0.7% ballast water, which is equal to 20 metric tons. Here we have a total of 160 metric tons of ballast water. The grain mainly has two hazards, namely settling and shifting. Both these factors affects the stability of the vessel. Two crucial things are required to be considered for carriage of grain. 1. The ship should have a valid document of authorization. And 2. The ship should have an approved grain stability booklet grain loading manual. Grain loading manual or grain stability booklet are class-approved information booklets, which gives the ship's officer various information with respect to grain loading on board. Following are the contents of grain loading booklet. Ship's particulars, light ship displacement and kg values. Table giving values free surface correction. Capacities and center of gravity of hold compartment. K&N curves and angle of flooding tables, where less than 40 degrees, at all degrees of heel. Curves or tables of hydrostatic properties suitable for the range of operating drafts. Curves, tables of volume, vertical center of volumetric, and assumed healing moments for every compartment, including the effects of the temporary fittings. Tables curves of maximum permissible healing for varying displacements. Details of scantlings or any temporary fittings. Loading instructions in the form of notes. A worked example for master. Typical service, loaded departure and arrival conditions. Flowchart of grain loading. Calculate the maximum quantity that can be loaded into the account the ship's dead weight, the load line zones she will pass through, the weights on board, draft limitations, etc. This process is called the dead weight calculation. 1. Distribute this cargo into the holds so as to have the maximum number of filled holds, but also considering the vessel's required draft, trim, stresses, etc. 2. Divide the cargo weight by the stowage factor to obtain the cargo volume depth of cargo in each hold. 3. From the healing moment diagrams in the grain loading booklet, Find out the volumetric healing moments for each hold. 4. Multiply the volumetric healing moments by the appropriate factor to compensate for the vertical shift of G. 5. Divide the corrected volumetric healing moments by stowage factor to obtain weight healing moments. 6. Add up all the healing moments for each hold to calculate total healing moments. 7. Compare the total healing moments with the allowable healing moments obtained from the grain stability booklet. 8. If the calculated total healing moments are lesser than allowable healing moments, proceed with the loading, else distribute the cargo and rework the calculation. And now back to our stowage plan. For this specific loading, the crew of the vessel did the calculation as explained before, and the vessel's grain healing moment, maximum allowed healing moment, hill angle and GOM are into permissible limits according to the vessel's grain booklet and International Grain Code. Here below, we can see the seasonal zone, summer, that the loading will be conducted, and the corresponding dead weight of the vessel in summer load line, which is 81,676 metric tons, as well as the TPC of the vessel in this specific dead weight, tons per centimeter of immersion, which here is 71.3 tons. Going to the right down corner, we can see the bending moment and the shear forces of the vessel. 66 and 52%. Allowable figures according to loadicator instrument of the vessel. Here we have the estimated displacement of the vessel once is arrived in the disport. The vessel will arrive in Dalian with 13 meters deepest draft in salt water with density 1.025. The vessel's displacement for 13 meters draft and 1.025 density will be 84,173 tons. Here above we can see the vessel's light weight, which is a standard figure, as the weight of the vessel when was delivered by the shipyard, which is 13,706 tons. Now, let's remind you a simple formula. Displacement minus the light ship is equal with dead weight of the vessel. So here, 84,173 tons displacement, minus 13,706 tons of light ship, we get a dead weight of 70,467 for draft 13 meters, and density 1.025. By extracting the weights that occupy vessel capacity, we can determine what capacity is left for cargo. So, 70,467 tons dead weight minus 160 tons ballast, minus 300 tons fresh water, minus 230 ton bunkers, minus 40 tons lub oils, minus 350 tons constant weights, minus 150 tons due to sagging or hogging. 68,740 tons of soybean is the estimated quantity to be loaded. Of course, all these calculation and the stowage plan, including loading and discharging sequence, are produced by the vessel's loadicator. Every vessel must be equipped with a custom-made computer software for loading calculation, approved by the class of the vessel. Each vessel is equipped with a unique computer software for loading calculation. According to its characteristics, it is called loadicator. And let's complete this presentation with one demo video of a loading software. Thank you for watching. I hope after this presentation you are more aware and have a better understanding for bulk carrier vessels and stowage plans. If any question, please do not hesitate to contact me. Bye.
Yeah.